Welcome everyone. Thank you for joining us for today's webinar. My name is Alberto Aguirre and I'm the sales manager at SensoMATCH, which is the leading provider of 3D surface optical profilers. Today, we are presenting quantitative measurement and automated bullet comparison using high-resolution optical 3D surface metrology. Presented by Cristina Cadevall, software manager at SensoMATCH. Just a little housekeeping before we get started. If you have any questions during the presentation, please type them into the question box in your GoToWebinar control panel. I will bring them up during the presentation at the end. Now, without further ado, we will turn the time over to Cristina.
Thank you, Alberto. I appreciate the introduction, and it's great, really great to be speaking to all you today. We will start the presentation. This is the two persons you are listening to, Alberto and myself. And okay, the summary of the presentation is to present first the background and motivation. Then we will present the methodology we are using for bullet comparison. We will show results we obtain, and then we will switch from the PowerPoint presentation to a video showing a demonstration of how this is working, and we will end with open time for your questions. Almost many of you know SensoMATCH, maybe others not. SensoMATCH is a company which we consider ourselves experts in surface metrology. We have more than 15 years of experience in this field, and we have sold more than 600 systems worldwide. Our expertise is in three techniques: confocal, interferometry, and focus variation, and we are quite unique in the fact that we can combine them all in one single instrument. The developments and the solution we are presenting related to bullet comparison measurements has been achieved or is possible due to the demands of the experts in the fields in which we cooperate for developing this solution. The main ones is the FBI labs, where Eric Smith and Jenny Stephenson are helping or in promote and facilitate the adoption of 3D metrology for firearm identification. Also, Iowa State University is active in this field and is also cooperating with us, as well as the NIST team related to firearms identification that is promoting advances in these fields. We also have some cooperation with the Spanish Guardia Civil Police in Barcelona. And finally, we are a part of the Open Forensics Metrology Consortium, an international consortium promoting a way to exchange and be able to use 3D regardless of the manufacturer of the instruments. Okay. From all these experts in the fields, we are using especially the NIST ballistics toolmark database created to help developers in this area. And also we are using the X3P format for exchange of 3D measurements among different instruments for comparisons. For those that are new in the field of firearm identification, I want to explain that the goal is to identify which firearm has shot a bullet from the marks that the barrel of the gun is creating on the bullet itself. The goal is to achieve, or we are seeking for speed and consistency in this firearms identification. Today, crime labs face this task to do firearms identifications with the common tool that is the optical side-by-side comparison microscope. This kind of tool was developed first in the beginning 20th century, in 190 and something, few years. And in this situation, the experts, the trained people, they are really performing good. And one of the key points for being able to do the firearm identification just by using side-by-side image comparison is that the lighting conditions are guaranteed or are almost the same for the two bullets under comparison. On the other side, there are some automated ballistic identification systems that been developed since 1990 year. And in this situation, the performance or the outputs are not so good, and mainly because the lighting conditions are not guaranteed to be equal between the different images uploaded to the database. These kind of systems are not very successful, especially if the bullets have different materials, or for example, the lead bullets that are more difficult than the copper ones. The bullet signatures are, by nature, 2D or 3D tool marks. This means that if we are doing 3D measurements, then we will be able to do quantifiable mathematical comparisons between any of these two surfaces. It is accepted and established that firearm identification based on 3D is more reliable than based on images, and will improve the correlation accuracy of the automated systems. In addition, 3D is able to help also in the side-by-side visual comparison. Here we will show a short video in which we show that our software, SensoCom, that is under development, is able to help on the visual comparison of two different 3D measurements. In this case, this is two lands of two different bullets fired with the same gun. Here in the two-dimensional view, we can see that there is a match when we really link the estimations. Okay, so here we see that from the 3D, we can create a rendering in software, which is able to do the same kind of help for the examiner that the side-by-side comparison microscope. But the powerful ability that 3D is providing for this discipline would be the quantitative 3D analysis. For that, the first thing we have to establish is the way to measure the degree of similarity between two 3D measurements. And here, what we are using, or what is recommended to use by the scientists, is public domain parameters. We have selected for our solution the cross-correlation function. Another question is if we will be using the full surface of the bullet or just some parts that have the marks that really make the difference between different barrels. It's what we call the individual characteristics surface. We have developed our solution for this individual characteristics analysis. To summarize the challenges in this discipline, there are thousands of comparisons of 3D measurements of land surfaces to be done in a reliable way and with traceability. And our answer to these challenges is a way or engine to do patch comparisons, the using of non-proprietary algorithms and parameters that will help in the reliability and traceability of the solution, and the implementation of reports with author data and bullets identifications, and finally, try to achieve the highest speed possible. Now we will move from the introduction to the methodology description. There is five steps. The first step it's today done manually and consists of measuring the line surface of the bullet. The second step consists on extract the individual characteristics surface from the surface measured. The third step is automated and consists of comparing the different individual characteristic surfaces using the cross-correlation function maximum parameter. The next step is to combine the individual line comparisons to create a score for the bullet comparison. And finally, there is the last step, which is again a manual step that has to be done by an examiner or an expert, that is to check the top match list that is showing the results of the bullet comparisons. This methodology, for example, has been applied with the Humvee test, which consists of 15 unknown bullets that are compared to 20 known bullets. And the timings are 11 hours for the manual bullet measurement and individual characteristics extraction. Then with just 4 seconds, we can calculate all the comparison scores. And finally, the expert will examine the results and bring to the side-by-side microscope the bullets he wants to verify. Now we will explain in detail every step of the methodology, the 5 steps. The first one consists of doing the line surface measurements themselves, the 3D measurements. For that, we are using our system we call SensoMATCH. This system has implements 3D surface net technologies, confocal, interferometry, and focus variation. And for the bullet measurements, it has been established that confocal technique is the most suitable one. In this system, what we do is to measure in the bottom part of the bullet. We will measure a section that can be narrow. We'll measure the striations on the surface. To measure one single bullet takes around 15 minutes. The second step is the individual characteristics extraction. For that step, we are using analysis software. And we are doing first, from the full surface, we do first one crop to eliminate the line shoulders and concentrate on the part with the striations. Then we are applying a roughness filter to remove the surface roughness. Then we do a font removal to remove the cylinder shape of the bullet. We then do a roughness filter to remove the deformations of the bullet. And we do a second crop of a narrow area with the striations, selecting the area that has where the striations are best marked. Finally, we save this IC surface, and this is the surface we are using for comparison. The third step, this step is taking, it has to be done manually. It takes around 3 minutes per day. The third step is the individual characteristic surface comparison. In this example, we have 2 measurements of the same one, doing at 2 different moments with the same instrument. And if we try to do the side-by-side comparison of these IC surfaces, we will find a deposition like this one, in which is showing a very good agreement. Now the goal is to do this instead of visually, to have this one by using the parameter. We are using the cross correlation of the mean profiles. This means that from the 2 individual characteristic surfaces, we take a mean profile and we compute the cross correlation mean profile. The result of that is a profile that has a peak in the position where the profiles are more similar. And the value of this peak that is constrained from 0 to 1 will tell us the degree of similarity. Here, these 2 IC surfaces have a similarity of 0.97. This is a very high similarity, close to 1. If we take 2 different lines of the same bullet, we will see that there is no position in which we can have a visual agreement, and the number, the CCF max, is telling also that there is no agreement. The value is as low as 0.3. To do one IC comparison, automatically is less than 1 millisecond. Next step is to take all the values of the comparisons of all the lengths of 2 bullets. In this slide, we see a diagram of 2 bullets, the blue bullet at the left and the red bullet at the right. We will measure all the lines in one bullet and all the lines in the other bullet with a microscope. We will get a 3D measurement for everyone. We will extract for everyone the IC characteristic surface, and then we will compute all the comparisons. The result is this matrix in which we get up to 36 different values of IC comparison between 0 and 1. What we will do first is to try to analyze this manually, and what we do is to try to highlight the high values. And now we have just, with the green square, highlighted the values that are above 0.5, and here we see that there is some agreement in here. And also we see that there is a sequence or phase between the agreements, and this is what has to be, because, for example, we see that the LAN 3 of blue bullet is very similar to LAN 1 of red bullet. And this means that if 3 is similar to 1, 4 has to be similar to 2. And we see that also in the sequence, except for this value. So an expert, to decide if 2 bullets are fired from the same firearm will take into account all the numbers in the matrix and look for high values, and they have to be in sequence. In this case, the expert will tell us that there is an identification. If we take another example of different bullets that have been fired with 2 different barrels, here we see that there is no single value above 0.5. In this case, there is no identification. The name for that situation is there is an elimination case. Next step is to try to do this automatically. For that, we have created what we call the sequence average maximum score, and this score is calculated by taking every possible single phase or sequence. For example, this principal diagonal in blue, we take this average and we note it here is 0.3. Then we compute the average of the second possible sequence, which is these 5 values plus this one here. And this is also 27. Next one is the green one, and this has most of the values in the sequence are high. So the mean is very high. So we do that for all the possible phases that are 6, and we take the maximum of these averages. And this score will only be high when the bullets have been fired with the same firearm. Next step is to see the performance of that with this study I mentioned with 15 bullets unknown compared to the 20 known. So we take the 20 known and we do a statistical study because we know in advance for these 20 known bullets which ones correspond to which ones. If we just take the cross-correlation function maximum of every single LAN, for the LANs that we know that have to match, we see the blue population, which is bimodal. This means that some of the LANs that should have a high value, they have a low value. And this happens because some aspects of the gun's performance, that sometimes the bullets are not well marked in all the LAN because changes in the diameter or other specific changes in this LAN. But the new score we have created for bullet comparison is much more efficient and robust and is able to separate totally the population of known match from the population of known matches. So we can use with this score, for example, for this kind of bullets, we can use 0.5 as an identification threshold with very safety. So with using this methodology, now we will show the results. What we have done to compute the result is to develop one software we call SensoMATCH. This software is what we call bullet comparison engine. It streamlines the bullet comparison task. It's using only published algorithms and is subject to open tests. The result files are the top match list, also all the score matrix for the bullets and for the individual lines. It has a training mode. We can manage bullets with missing lines. It's also possible to use customized templates for the comparison, and also is accepting any kind of 3D outputs by using the X3P format. So it's not linked to our systems. This kind of software can be used with any 3D measurement. This software is being used today at FBI labs and Iowa State University and is commercially available. This is a video in which we are comparing the 50 unknown bullets to the 20 known bullets with the SensoMATCH software. The first step is to select the folders where the bullets are placed. And next step, to give a name to the study and click compare. And with just a few seconds, we get the comparison result of these bullets in form of CSV files. For example, now we will just show this is the top match list at the left and the scores list or matrix at the right. Now I will just show the same score matrix with more nicer view. So you take the CSV file, go to Excel, and you can create a nice view for that. Here we see all the rows is the 20 known bullets. So there are 10 barrels, and every barrel is, let's say, defined by 2 different bullets. And then we have the 15 unknowns, and we see in green the values that are above 0.5. And here we see at the end, at the bottom, we see the reference of the results of this test. And we see that the result is matching. So the automatic firearm identification using our system for 3D measurements and our comparison software is achieving the same results as the examiners are able to achieve. The next step we did is to take in the 15 unknown bullets. In this example, we were using all the lines for all the bullets. In the next slide, we are showing a case we have created a study in which we have been removing lines from some of the bullets. So, for example, bullet B still have 6 lines, but bullets X, Y, and Z have only 1 line. Here, the performance is kept very well, but we see that only in the bullet Y, there is no identification. The good point here is that we are not able to identify, but also we don't give a false positive. And the reason for this, when you go to inspect this line, is that the remaining line was very poor mark. Okay, so it has, let's say, an examiner with the same kind of information would also not be possible to make the identification. So in this case, we are identifying 14 bullets from out of 15. Finally, I want to summarize what we have been presenting. We have created a new methodology for bullet analysis using high-resolution optical 3D surface metrology. It consists on separating the IC extraction step from the IC comparison, which streamlines the batch comparisons and allows lighter database. Also, we have been using and creating a customizable IC extraction template. Current template is performing very well with pristine copper bullets. Also, we have been using the well-known IC comparison value, which is the CCF max from mean profiles. We have been developing a comparison score for bullet comparison. We call it SUM, which is the sequence average maximum. And finally, we have created a software for testing all this and doing comparisons. This is a tool for R&D teams, and very soon could be a tool for casework examiners. Finally, so here it ends the PowerPoint presentation. We will switch to the video, which is a demonstration on how this is working, and then we will move to questions. Okay, so we have seen the video. This video was presenting from one single measurement of one of a bullet to how we extract the individual characteristics and then how we compare that single line to the two full measurements of the two bullets fired with that gun. So we see at the end that the correlation is very high, so this line is matching to both lines, bullet 13 and 14, and is more equal to bullet 14, which is the same bullet where the line was made. So here we finish the explanation and we're moving to the questions part.
Thank you, Christina, for your information. If you couldn't watch properly the video, you can find the same video with music in our YouTube channel, SensoMATCH YouTube channel, and also if you want, we can send the video to YouTube. So now we will go ahead and take some time for questions. Just a reminder, please be sure to type your questions into the question box in your GoToWebinar control panel. So it looks like we have a few questions. So John Marshall is asking, are you able to scan the entire bullet surface and provide a single CCF value instead of scanning each line separately and calculating individual CCF values?
Okay, in our approach, we have been working to have one single value for every bullet comparison, which is what we call the SAM score. And to get this score, we are using the individual comparisons of the one-to-one comparison. So today, our approach is not to measure one single one single 3D measurement of a surface around the bullet, but to measure every line as a 3D, and then from that get the individual characteristics surface. And from the set of all one-to-one comparisons, we are getting one single final value. That is the similarity between two bullets.
So let me do one thing. So John Marshall, I will open the microphone for you if you want to comment anything else.
We are trying, but it's not. Okay.
No. Hello, John. Mr. Marshall.
Hello, can you hear me?
Yes,
we can hear you.
Everyone is hearing, I think.
Is listening, yes.
No, that was great. That answered my question. Thank you.
Okay.
Okay, so we'll go to the next question. I switch off your microphone if you don't mind. Okay, even the next one is yours too.
Yes.
I think all the people can see the questions. So.
Can you repeat just?
So next question is SensoMATCH for sale or on its own, and it can be used with another 3D scanner?
Yes, this would be the approach that we see SensoMATCH as a solution for firearm identification from 3D measurements. So we will, that software will be reading our proprietary file format and some others. And one of the main ones would be the X3P format that Open Forensics Metrology Consortium and NIST are promoting as the standard way to exchange 3D from different systems.
Okay, John, it's clear?
Yeah, absolutely. Thank you.
Okay, thank you. Then next one, Dave Estella, he was asking, is there a time comparison between the speed of this Humvee test versus the traditional examiner methodology, comparison microscope?
Well, no, because the only timing comparisons or calculations we made are all based on using our 3D. So we had, so we didn't ask really examiners what is the timing. But I guess it will be very long.
Okay, if Stella is typing, thanks. So you can move to the next one. Again, John Marshall, have you tested the SensoMATCH software on damaged bullet or bullet
fragments?
Or bullet fragments? And if so, how has it performed?
The only approach to that was the the slide I show in the results, the last results slide which we were showing, which were the results. Next one. Okay, just one moment. Okay. So here in this slide we are showing results of what happens when we start to have less and less lengths measured for the bullets. By sure we should do also real examples by getting damaged bullets, but it's not up to today. It has not been possible because normally these are evidences from real cases, so we haven't had access to that. For the results we get in that experiment, we think that if you have a land or a fragment that is well marked, it will be still possible to do the identification.
And let me open the microphone. From John. John, any comments on that?
No. So right now, in terms of the research, the Hamby test is the only one you guys have done so far through the SensoMATCH software.
As a, let's say, as a complete study that is worth mentioning, yes, because we had some. Well, ourselves, we had only access to. Okay, let me explain it well. So for demonstrating SensoMATCH, we did the Hamby test by downloading the measurements from the NIST database. Okay, and we will be downloading and testing any other kind of set that NIST is sharing in the database. This is one side of the thing. On the other side, we have been doing measurements for potential customers and people interested in the solution, but few bullets every time. So it's not worth mentioning, let's say, the results for that. And we are involved in a new study that is going on. So, for example, today I received a set of 34 bullets. We will try to measure here in SensoMATCH. So we are active and very aware that we will have to do even more from our side. On the other side, FBI has been using our technology since I think it's 3 to 4 years. And they have been publishing studies based on confocal measurements using our technology. And this is a much wider study than the Hamby.
Excellent, thank you.
Okay, next question, again from John. Have you developed the automated stage for scanning the bullet, or is this still a manual process?
Okay. So this is a very nice question because we want to share up with all of you that we are working on the automation of the scanning, because today this is one of the bottlenecks for the adoption of this technology, and we will be having a first prototype by summer, and later transform it into a commercial module that you could add to the microscope.
Sorry, you said by summertime?
But in let's say the first prototype, so as a commercial product, it will take a little longer because we will have to, or we have plans to verify the performance of that prototype with FBI labs, and most likely we will have to do some improvements. Normally it happens. So to have the final commercial module, it will take maybe 1 year or so.
Okay. Excellent.
We will see.
Okay, excellent. Thank you very much.
But this module, we plan that will be a kind of complement to the microscope. So existing 3D measurement stations like these NIOX will be ready to operate for that.
Excellent. Thank you.
Okay. Next question, Nick Petraco. What does the SensoMATCH software do with dropouts and layers from the initial confocal or focus variation scan? Fill them in, if so, how?
Okay, so we are keeping the dropouts or non-measured points as non-measured. But then, as we are using the mean profile, normally this will lead that when we compute the mean profile, the dropouts are kind of not taken into account for the mean, and you finally get to a mean profile that normally has 100% of points in the profile. Okay, this is one thing. And for the outliers, the filterings, the filter we say that is removing the surface roughness, which is a waviness filter, or in other words, a filter that is removing the highest frequencies. It's taking out the outliers from the surface. So in the IC characteristic surface that is filtered, we don't have significant or outliers that would make a difference for the final score. Nick, do you have now your microphone open if you want to?
Yeah, no, that's fine. I understand. Yeah, now I understand what you do.
Okay, thank you.
Thanks.
So also Bill Henderson from SensorFire US has a microphone on. If Bill, if you want to add any comment, yes, please feel free.
Okay. So far, I'm doing great.
Okay, thank you.
Okay.
So next question, Andre Costello. We have been experimenting with fragments. How wide are your lands?
Okay, our lands are around 1.9 millimeter wide with the bullets we have been working with.
So, Andrew, you have the microphone.
Yeah. Thank you. Yeah, we experimented with fragments yesterday. We just can't get the lands to get that wide. We're around 0.6 millimeter for a capture at 20 times. Okay, but we were looking into that. So you're 1.5 millimeter?
1.9, but it depends on the barrel.
Okay, so assuming it's a 9 millimeter round?
Yeah.
Okay, so 6. Okay, all right. So you get the circumference. All right, because that's one of the problems we were struggling with yesterday. But if you want, I can get you bullets, pristine bullets, match the fragments. I have no shortage of them.
So you can share or let us to do measurements on fragmented bullets.
Yes.
This is a very nice offer. So we will contact you. And
how many barrels you need?
How many?
How about this? I'll email you.
Yeah, sure. Thank you, Andrew. We will keep in contact and see if we can do some findings on that. Thank you.
This is Bill Henderson. I'm actually at Iowa State today with a couple of the guys from NIST they're working on this project, and they're in discussion of getting literally hundreds and hundreds of bullets from hundreds of barrels, thousands of bullets. This is going to take some time, but we're working on developing. So far we've measured and tested and compared, individual bullet sets in many cases, and we've done the Hamby test in terms of a full sequence. And the process right now is developing the database and the statistical analysis of large volumes of bullets for comparison. And that process is going underway. And as we do that, we're going to also introduce things like fragments and parts and things like that. And I can talk to you about that later. We're welcoming to get as many bullets from as many sources as we can. Both combination of local as well as reference sets and things like that. So there's a lot of work going on in a lot of places over the next few months on this.
Okay, thanks, Bill, for your contribution.
Okay. So, Mr. Borburger lifted his hand. Hello, Mr. Borburger, do you have any questions?
Hello, yes, thank you. It would be interesting to compare, looking at your slide 27, it would be interesting, no, it was there, right, to compare the topographies of bullet Y and bullets pair 6 to see in detail why it fails. And then conversely, it would be interesting to look at the topographies of bullet D and bullet 5, which scores so high. Just curious to see how why that is so good.
So we will do the following. I will use the new software we developed, SensoMATCH, which will allow the visual comparison, and I will just share with you and all the people in the webinar this new like a small video showing the two cases. So one case where one line is very high, and another case you need to have a line that should be high and is not.
Yeah, right, great.
Ed, this is Bill again. I was sitting next to Eric Hare, who's done a lot of work on the matching algorithms. And when this came up, I mentioned to the team here that for bullet Y, if you took any of their 5 lands from that bullet and did them individually, you would get a match. That one land was very poorly marked. And when I mentioned that, Eric looked at me and said, he goes, I know exactly which land that is. I know just how big it looks. Essentially, the way we look at it is, the mathematical comparison is simply a way to supplement what examiners are doing and do it kind of automatically and quickly. And if you took that same land and gave it to an examiner, they'd probably find the same thing, that it was inconclusive. They couldn't determine a match, but the rest of the bullet would be perfectly fine. It's just it's one of those lands that was very poorly marked based on either it just didn't go through the barrel cleanly, that one side.
This result comes from a SAM comparison, which I thought was looking at all 6.
Yeah, but what happens is it was bullet Y. It was the unknown. That one land on the unknown bullet had a poor marking, and so it doesn't matter what you compare it to. That can compare it to anything, and it will always get a poor match.
Yeah.
Aren't there 6 lands on bullet Y?
Oh, but in this case, we only had 1, and it was a bad one.
So if we switch to slide 26.
Oh, I see. Great.
Lands, and we have a score which is quite high. So, for example, in terms of the SAM parameter, the one that has less score is bullet Q. The bullet Q has, let's say, a poor SAM value, especially bullet for barrel 1, barrel 10, bullet 1. Okay, and in the opposite, it's the bullet D is having the highest SAM score.
Right. Okay.
It's using all the lines for the 20 knowns, and also all the lines for the 15 unknowns. And in the next slide, in 27, then here in the unknowns, we have been removing randomly some lines from the unknown bullets and see what happens.
Very good. Thank you.
Thank you. Thank you, Mr. Bosbuker. So, we have another question from
Dion
Christoph. Any testing on polygonal bullet samples?
Okay, here we have some samples. We have, I think, 6 or 7 samples, and they come from the Spanish police, and we have been starting to take a look on that samples that have a very weak mark. And the same analysis template for IC extraction is not valid. So we have in our list to do to try to guess which is the most suitable acquisition parameters, and also how the template for extraction has to be tuned for that kind of bullets. But it looks very like a difficult task to get the highest score. But we will do that, but in a later time. Dion, you have your audio open if you want to give your opinion.
No, that's perfect. I really appreciate that. I was just curious if there had been a viewpoint from non-conventional style bullets. Thank you so much.
Okay, thank you.
Okay, thank you.
Okay, so now it looks that we have covered all the questions. Alberto.
So if there is anything else you want to cover before wrap?
Well, I think we are okay, and it has been a real pleasure to share this time with you, and we really thank you for your attention and your time.
Yeah, great. Thank you, everyone. We appreciate for being here. So soon as we close, we will send you the video and the presentation. We will share that with you. And if you have any other question in the presentation, you have our mail, so you can contact us and we'll try to reply to your question. Okay. Thank you and enjoy the day.
Bye-bye.
Bye-bye.